everyone, welcome back to my channel. In this video, we study about application level part of differential equation, that is Newton's law of cooling. First, let us understand the statement of Newton's law of cooling. Let us suppose capital T be the temperature of a body and T naught be the temperature of a surrounding medium at any time small t, then by the property of Newton's law of cooling, the rate of change of temperature of a body is directly proportional to the difference between temperature of a body and the surrounding medium. So this is a statement of Newton's law of cooling. That is, Newton's law of cooling states that the rate of change of temperature of a body is directly proportional to the difference between temperature of a body and the surrounding medium. We can write the differential equation as dt by d into small t is directly proportional to t minus t naught, where t is a temperature of a body and t naught is a temperature of a surrounding medium at any time t. So the rate of change of temperature of a body is directly proportional to difference between the temperature of a body and the surrounding medium at any time t. So this is a statement of Newton's law of cooling. Or we can write it as dt by d into small t, which is equal to some minus k into t minus t naught, where minus k is nothing but a proportionality constant. So here is a proportionality sign. So to remove the proportionality sign, we have write the symbol as minus k. So dt by dt, which is equal to minus k into t minus t naught, where minus k is some proportionality constant. Next step, take this dt to the right hand side. We get as dt, which is equal to minus k into t minus t naught into dt. Next, take this value to the left hand side. We get as 1 by t minus t naught into dt, which is equal to minus k into dt. This is because we have separate the capital T term and the small letter t term. We get the value as 1 by t minus t naught into dt in one side, which is equal to minus k into dt. Next, we can apply the integration on both the sides. We have to apply integrating on both the side means integration of 1 by t minus t naught into dt, which is equal to, here minus k is constant, take outside the integration, into dt. We have to integrate this value with respect to capital T and we have to integrate this value with respect to small t. Here we have to integrate this value with respect to t means here 1 by t minus t naught. Integration of 1 by t minus t naught is log of t minus t naught, which is equal to minus k is constant, take as this, into integration of 1 into dt. Here no value is nothing but 1 into dt. Here integration of 1 with respect to t is small t itself, plus some integration constant c. Now in the next step, we have to take this log on right side. We get as t minus t naught, which is equal to exponential power of minus kt plus c. So if we take this log to the right hand side, that becomes exponential power of this value, that is minus kt plus c. Next step, take this t naught to right hand side. We get the value of t as t naught plus exponential power of minus kt plus c. We have to split this value as e power minus kt into e power c. Here bases are same, adding the power, this value becomes like this, exponential power minus kt into exponential power c. Next, we can take this value as t is equal to t naught plus, here exponential power c is some constant value. We can take that constant as lambda into exponential power minus kt as it is. Here lambda is exponential power c. So this is a formula we obtained from the statement of Newton's law of cooling, that is T is equal to T naught plus lambda into exponential power minus kt, where T is a temperature of a body and T naught is a temperature of a surrounding medium at any time t. We shall see how to apply this formula in coming problem. Next, we shall understand what are all the applications of Newton's law of cooling in engineering. First, in electronic and electrical engineering, in particularly in thermal management of electronic devices, Newton's law of cooling is used to model the cooling behavior of electronic components and optimize the design of heat sinks and cooling systems to prevent overheating in devices like computers, servers, and power electronics. In mechanical engineering, in particularly in heat exchanger design, engineers use Newton's law of cooling to design and analyze heat exchangers for applications like automotive radiators, HVAC systems, and industrial processes. It helps in determining the heat transfer rates and optimizing the size and configuration of heat exchanger systems. In civil engineering, particularly in building thermal analysis, Newton's law of cooling is employed in analyzing the thermal behavior of buildings. This is crucial for designing heating, ventilation, and air conditioning HVAC systems to maintain comfortable indoor temperatures while optimizing energy efficiency. In the field of aerospace engineering, particularly in spacecraft thermal control, Newton's law of cooling is used to predict and manage the thermal environment. It helps engineers design systems to dissipate or retain heat as needed during different phases of a mission, such as space travel or re-entry into the Earth's atmosphere. In the field of biomedical engineering, particularly in medical device design such as thermal therapy equipment or temperature controlled chambers, Newton's law of cooling is used to ensure that the devices operate within safe temperature ranges to avoid harm to patients or damage to biological samples. In automotive engineering, particularly in engine cooling systems, Newton's law of cooling is utilized in the design and analysis of engine cooling systems. It helps engineers optimize the performance of radiators and cooling systems to maintain the appropriate operating temperature for internal combustion engines. In environmental engineering, particularly in wastewater treatment, Newton's law of cooling may be applied to model the cooling of wastewater or sludge, helping engineers design system for effective treatment and disposal. So these are all the important applications in various fields of engineering. So it is very important to study Newton's law of cooling. Next, let us solve some important question paper problems on Newton's law of cooling. Here is the first problem. A copper ball originally at 80 degrees Celsius cooled down to 60 degrees Celsius in 20 minutes. If the temperature of air is 40 degrees Celsius, what will be the ball after 40 minutes from the original? Here we have to solve the problems according to Newton's law of cooling. So first take the given data. Here they have mentioned a copper ball originally at 80 degrees Celsius. Here first at room temperature the copper ball will be at 80 degrees Celsius. If we cool down that copper ball, that reduced to 60 degrees Celsius in 20 minutes. If the temperature of air is 40 degrees Celsius, then we have to find what is the ball after 40 minutes from the original. That is, what is the temperature of the ball after the 40 minutes from the original value. Here first take the given data. Here they have mentioned the copper ball originally at 80 degrees Celsius. That means at T is equal to 0, we get the value of temperature of a copper ball as 80 degrees Celsius. Here they have mentioned the temperature of air is 40 degrees Celsius. That is, the temperature of air we can take it as T0. T0 value is temperature of air, that is given by 40 degrees Celsius. Here the copper ball originally at 80 degrees Celsius means at time T is equal to 0. The value of copper ball, that is the temperature of a copper ball is 80 degrees Celsius. At time 20 minutes, the copper ball, it reduced the temperature to 60 degrees Celsius. That means at time 20 minutes, the temperature of a copper ball is 60 degrees Celsius. We have to find what will be the ball after 40 minutes from the original. That means what will be the ball's temperature after 40 minutes. That is, we have to find at time 40 minutes what is the temperature of a ball. That is, we have to find the T value. Let us suppose T be the temperature of a copper ball and T0 be the temperature of air at time T. We know that from Newton's law of cooling, the temperature of a function at any time T is given by T is equal to T naught plus lambda into exponential power minus K into T. Here, to find the temperature of a ball after 40 minutes, we have to find, in the first step, we have to find the lambda value. For that, substitute T naught value. They have given the temperature of a air value T naught is given by 40 degrees Celsius. Substitute that value here, we get as T is equal to T naught is 40 plus lambda into exponential power minus K into T. Call this as equation number 1. Next step, we have to substitute the given data over here, that is at the time T is equal to 0, that is initial at time T is equal to 0, the temperature is given by 80 degrees Celsius. So at T is equal to 0, substitute T value as 80 degrees Celsius. So substituting T value as 80, which is equal to 40 plus lambda into exponential power minus K into T value is 0. Here small t is the time and capital T is the temperature of a copper ball. We know that at time T equal to 0, temperature of a copper ball is 80 degrees Celsius. So substituting T value as 80, we can take this as 80 is equal to 40 plus lambda into exponential power minus K into, here small t is time, that is 0. We know that exponential power 0 is 1. Hence we get, this value becomes 1. Hence we get lambda value as, here take this 40 to the left hand side, 80 minus 40 is 40. Hence we get the value of lambda as 40. Here first step is completed, that is to find the lambda value means substituting the given data. Here they have given the temperature of the air is given by 40 degrees Celsius. Substituting that value, again we have to take the given data at time T is equal to 0. The temperature of a ball is 80 degrees Celsius. Substituting T as 80 and at time T is equal to 0, we get a lambda value as 40. Once we obtain a lambda value, substituting this lambda value over equation 1, we get, now we have to substitute lambda value as 40 over here. We get the equation 1 as T is equal to 40 plus, here lambda is 40 into exponential power minus kt as it is. So the equation reduces to this. Call this as equation number 2. Here we obtain this equation at the data T is equal to 0. We get a value of T as 80 degrees Celsius. Next, we have to take this value, that is at time 20 minutes T is 60 degrees Celsius. That is at time 20 minutes the temperature of the ball here reduces to 60 degrees Celsius. Hence the equation 2 reduces to, here in the place of capital T we have to substitute as 60, which is equal to T naught is 40 plus lambda is 40 into exponential power minus K into, here T is, that is small t is 20. Next step, take this 40 to the left hand side, 60 minus 40, that is 20, which is equal to 40 into exponential power minus 20 into K. Take this value to the left hand side, that becomes 20 divided by 40. We know that 20 divided by 40 is 0.5, that is 0.5. That's our exponential power minus 20k value. We are doing this procedure because first step we have to find lambda value. Next step we have to find k value. Further, we have taken the second data, that is at time T is equal to 20 minutes. We have to substitute the temperature of a ball is 60 degrees Celsius. That is 60 is equal to 40 plus 40 into exponential power minus 20k. Take this 40 to the left hand side. 60 minus 40 is 20, which is equal to 40 into exponential power minus 20k. Hence we get exponential power minus 20k value as 0.5. Next step, we have to take log on both the side. We get, here taking log on both the side means we get as log of e power minus 20k. Here we have base e, which is equal to log of 0.5 to the base e. We know that from the logarithmic formula, log of m power n, we can split it as n log m. So this is of the form log m power n. So we can split this value as minus 20k into log e to the base e. Also we know that log e to the base e value is 1. Hence we get the value on the left hand side as minus 20k. That is minus 20k. This is of the form log of m power n. We can split it as n log m. That is minus 20k into log e to the base e. Also we know that log e to the base e value is 1. So substituting that value we get as minus 20k in the left hand side, which is equal to log of 0.5 to the base e. We know that Log of x to the base c, we can write it as ln of x. Log is different, ln is different. Log of x to the base c, we can write it as ln of x. Here this is of the form log of x to the base c. Here x is 0.5. Hence we can substitute as ln of 0.5. Log of 0.5 to the base c is ln of 0.5. We can take, using the scientific calculator, we can obtain the value of ln of 0.5 as minus 0.6931. Ln of 0.5 value is minus 0.6931. That is our minus 20k value. Take this minus 20 to the right hand side, that becomes divided by minus 20. Hence, we get k value as minus 0.6931 divided by minus 20. We get a value of k as 0.03465. This is a value of k. Once we substitute the second data value, that is t is equal to 20 minutes, t value becomes 60 degrees Celsius. In equation 2, we get a value of k. Once we obtain k value and lambda value, substitute in equation 2, we get as equation 2 is t is equal to 40 plus lambda is 40 into exponential power of, here k is this value, that is minus k value is 0.03465 into t. Here we have to write the positive or negative sign carefully. This is equation 2 is t is equal to 40 plus 40 into exponential power of minus kt. Here k value is 0.03465 into t. This is a value of t. Also they have given, finally we have to find the value of this t, that is the temperature of a copper ball when the time is 40 minutes. At time t is equal to 40 minutes, we have to find the temperature of a copper ball. For that, substitute here t value as 40, we get as t is equal to 40 plus 40 into exponential power of minus 0.03465 into, in the place of small t, we can substitute as 40, that is t value is 40 minutes. We have to find the capital T, that is temperature of a copper ball at time 40 minutes. So in the place of small t, substitute as 40, we get as t is equal to 40 plus 40 into, here exponential power, multiply 40 inside, minus 0.03465, we get a value as minus 1.384. Here exponential power of, multiply this value, we get as minus 1.384. Next, we calculate this value 40 plus 40 into exponential power of minus 1.384 in a scientific calculator. We get a value of t, that is temperature of a copper ball at time 40 minutes, we get as 50 degrees Celsius. This completes the problem. We shall move on to another problem so that you can understand in a better way. The temperature of a air is 30 degrees Celsius, cools from 100 degrees Celsius to 70 degrees Celsius in 15 minutes. Find how many long will it take for reach the temperature of 40 degrees Celsius. First, take the given data. The temperature of a air is 30 degrees Celsius. That means T0 value is 30 degrees Celsius. Cools from 100 degrees Celsius to 70 degrees Celsius in 15 minutes. That means initially at time t is equal to 0, the temperature is t is equal to 100 degrees Celsius. After 15 minutes, that is at time t is equal to 15 minutes, t value becomes 70 degrees Celsius. Find how many long will it taken for reach the temperature of 40 degrees Celsius. That means we have to find at t is equal to 40 degrees Celsius, what is the time taken to reach the temperature 40 degrees Celsius. That is, we have to find the small letter t value at t is equal to 40 degrees Celsius. Let us suppose capital T be the temperature of a metal ball and T0 be the temperature of the air at time t. We know that according to the Newton's law of cooling, we get a formula as t is equal to T0 plus lambda into exponential power minus kt. Here to solve this problem, first step we have to find the lambda value. Once you obtain the lambda value, substituting the given data, we get a value of k. After finding lambda and k value, finally we have to find the what is the aim to find the Newton's law of cooling. For that, substitute T0 value, that is the temperature of air is T0. We get a value as 30 degrees Celsius, that is T is equal to 30 plus lambda into exponential power minus KT. Call this as equation number 1. Next we have to use the given data, that is at T is equal to 0 degrees Celsius, we can substitute T value as 100 degrees Celsius. That is initially at time T is equal to 0, we get a temperature of a metal ball as 100 degrees Celsius. Substituting T as 100 and this small t as 0, we get as 100 which is equal to 30 plus lambda as it is into exponential power minus k into t value is 0. We know that 0 into anything is 0 itself, hence exponential power 0 is 1. Hence we get lambda into 1 which is equal to, here take this 30 to the left hand side, that is 100 minus 30, we get a value of lambda as 70. Substitute lambda value as 70 in equation number 1, we get as t which is equal to 30 plus lambda value 70 into exponential power minus kt. Call this as equation number 2. Once you obtain lambda value as 70, next we have to take the condition at t is equal to 15 minutes, we get a value of temperature of a metal ball as 70 degrees Celsius. Now substitute t value as 70 and this small t value as 15 minutes. In equation 2, we get as 70 which is equal to 30 plus 70 into exponential power minus 15 into k. That is k, t value is 15 into k. Take this 30 to the left hand side, 70 minus 30 is 40 which is equal to 70 into exponential power minus 15k. Take this 70 to the left hand side, we get exponential power minus 15k value as 40 divided by 70, and taking log on both the side, we get a value of minus 15k which is equal to log of, here 40 by 70 value is 0.571. Next step, log of 0.571 to the base c, we can take it as ln of 0.571. We know that ln of 0.571 value is minus 0.5603. That is a value of minus 15k. Take this minus 15 to the right hand side, we get a value of k as 0.03735. This is a value of k. Here, first step, we have to find lambda value. Once we obtain the lambda value, substituting the conditions at time t, we get a value of temperature of a ball. Substituting in the equation 2, we get a value of k as 0.03735. Once we obtain lambda value and k value, finally we have to find the at what time taken to reach the metallic ball for a temperature of 40 degrees Celsius. That is, substituting all the values in equation 2, we get as, here t is 40 which is equal to t naught is 30 plus lambda value is 70 into exponential power of k value is 0.03735, that is minus 0.03735 into t. We have to find the t value here, that is at what time we get a temperature of a metallic ball as 40 degrees Celsius. Here take 30 to the left hand side, we get as 10 which is equal to 70 into exponential power of minus 0.03735 into t. Next step, take this 70 to the left hand side, that is 10 divided by 70, that becomes 1 by 7 which is equal to exponential power of minus 0.03735 into t. Next step, to obtain the value of t, taking log on both the side, we get as, here this value becomes log of exponential power of minus 0.03735 into t, we get as minus 0.03735 into t which is equal to, here log of 1 by 7 to the base c, we can take it as ln of 1 by 7 is 0.1429. Once you obtain ln of 0.1429 in the scientific calculator, we get as minus 1.9456. Ln of 0.1429 is minus 1.9456. That's a value of minus 0.03735 into t value. Take this value to the right hand side, that becomes t is equal to minus 1.9456 divided by minus 0.03735. We get a value of t, that is small letter t is the time taken to travel temperature of 40 degrees Celsius is 52 minutes 9 seconds. This completes the problem. We shall move on to another problem. A body in air at 25 degrees Celsius cools 100 degrees Celsius to 75 degrees Celsius in 1 minute. Find temperature of a body at end of 3 minutes. Here, first take the given data. Here, the body is in air at 25 degrees Celsius, that is T0 is 25 degrees Celsius, cools from 100 degrees Celsius to 75 degrees Celsius in 1 minute. That means at T is equal to 0, initially the temperature is 100 degrees Celsius. After 1 minute, that is at T is equal to 1 minute, the temperature is 75 degrees Celsius. We have to find the temperature of a body at the end of 3 minutes. That is, at T is equal to 3 minutes, you have to find the temperature of a body. We know that from Newton's law of cooling, we have a formula T is equal to T0 plus lambda into exponential power minus kT. Here, first our aim is to find lambda value. Using lambda value, we have to find K value. After finding lambda and K value, we can find the value of temperature of a body. Here, substitute T0 value as 25 degrees Celsius, we get as T is equal to 25 plus lambda into exponential power minus kT. Call this as equation number 1. Here, take the given data. At T is equal to 0, the temperature is 100 degrees Celsius. Substituting this value, here we get as T is 100, which is equal to T0 is 25 plus lambda into exponential power minus K into, here small letter T is 0. Here 0 into K is 0. Exponential power 0 is 1. Hence we get lambda value as, you take this 25 to the left hand side, that is 100 minus 25, that is, we get a value of lambda as 75. Once we obtain lambda value, substitute this lambda value in this equation number 1, that is equation number 1 becomes T is equal to 25 plus, here lambda is 75 into exponential power minus K into T. Call this as equation number 2. Next, take the data at T is equal to 1 minute, the temperature is 75 degrees Celsius. Substitute T value as 75 degrees Celsius and T is 1 minute. We get as 75, which is equal to 25 plus 75 into exponential power minus K into T is 1. Here take this 25 to the left hand side, we get as 75 minus 25 is 50, which is equal to 75 into exponential power minus K. Next step, take the 75 to the left hand side, that is 50 divided by 75, we get a value of exponential power minus K as 0.6666. Next, taking log on both the side, we get as in the left hand side log of exponential power minus K, we get take it as minus K, which is equal to log of 0.6666. That is log of x to the base c, we can take it as ln of x, that is ln of x value is 0.666, that is our minus K value. Here using scientific calculator, ln of 0.666 we can take it as minus 0.4064, that is our minus K value is minus 0.4064, hence we get a K value as plus 0.4064. This is our K value. Once you obtain lambda value and K value, hence the equation 2 becomes, at the time T is equal to 3 minutes, equation 2 becomes E is equal to, here T0 is 25 plus lambda is 75 into exponential power, here K is minus 0.4064 into 3. Here K value is positive sign. Here in the equation 2 we have exponential power minus K, hence we get minus K is 0.4064 into T is 3 minutes, that is T is 3. Next step, multiply 3 into 0.4064, we get as T is equal to 25 plus 75 into exponential power minus 1.2192. Next step, exponential power minus 1.2192, we can take it as 0.2954. Here using calculator, we get a value of exponential power minus 1.2192 as 0.2954. Next, multiply this 0.2954 into 75 plus 25, that is T is equal to 25 plus this value becomes 22.159. Adding these two values, we get a value of temperature of a body as 47.16 degrees Celsius. This is the temperature of a body at T is equal to 3 minutes. This completes the problem. Let us move on to another problem. A bottle of mineral water at a room temperature 72 Farad is kept in refrigerator where the temperature is 44 Farad. After half an hour, water cooled to 61 Farad. What is the temperature of a mineral water after another half an hour? Here they have mentioned the temperature in Farad. Take the given data. Here the bottle of mineral water at a room temperature 72 Farad is kept in refrigerator where the temperature is 44 Farad. That means the temperature, that is T0 is 44 Farad. Initially at T is equal to 0, the temperature of the bottle of a mineral water is 72 Farad. After half an hour, the water cooled, that is at T is equal to half an hour means 30 minutes. The temperature is 61 Farad. We have to find what is the temperature of a mineral water after another half an hour. That means at time T, here first half an hour, that is 30 minutes. Along with this 30 minutes, we have kept that mineral water for about another half an hour, that is T is equal to 60 minutes. We have to find the temperature of the mineral water, that is capital T, we have to find at small letter t is equal to 60 minutes. The procedure is same as before. We know that from Newton's law of cooling, we have T is equal to T naught plus lambda into exponential power minus kT, where T naught is the temperature of the air, that is T naught is equal to 44 Farad. Substitute T naught value here, we get as T is equal to 44 plus lambda into exponential power minus kT. Call this as equation number 1. Next, take this condition at T is equal to 0, T value is 72 Farad. That is at T is equal to 0, substitute T value as 72, we get as 72 which is equal to 44 plus lambda into exponential power minus k into here T is 0. Here this value becomes 1. Lambda into 1 is lambda, which is equal to 72 minus 44. We get a value of lambda as 28. Once you obtain the lambda value, substitute this lambda value in equation 1. That is equation 1 becomes T plus 44 plus lambda is 28 into exponential power minus kT. Call this as equation number 2. Once you obtain the equation number 2, we have to take the given data, that is at T is equal to 30 minutes, substitute T value as 61 Farad. That is at T is equal to 30 minutes, T value becomes 61 Farad. Substitute this value in equation 2. We get as 61 which is equal to T naught is 44 plus lambda is 28 into exponential power of minus k into T value is 30 minutes, that is 30. Take this 44 to the left hand side, that is 61 minus 44, we get as 17 which is equal to 28 into exponential power minus 30k. Also take this 28 also to the left hand side, that becomes 17 divided by 28. We get a exponential power minus 30k value as 0.6071. Next step, taking log on both the side, we get as minus 30k which is equal to ln of 0.6071. Using calculator, we get a ln of 0.6071 value as minus 0.49906. That is our minus 30k value. Take this minus 30k to the right hand side, we get a value of k as 0.0166. Once we obtain lambda value and k value, therefore the equation 2 becomes T is equal to 44 plus 28 into exponential power of minus 0.0166 into small letter t. Here we have to find if the mineral water is kept another half an hour at same temperature, then we get a T value as 60 minutes. Here already we have kept it for 30 minutes. Again, along with this, we can kept another half an hour. That means the T value becomes 60 minutes, not 30 minutes here. It is T value becomes 60 minutes. At T is equal to 60 minutes, we have to find the temperature of a mineral water. So substituting all the values, that is T is equal to 44 plus 28 into exponential power of minus 0.0166 into, in the place of T we can substitute as 60. Multiply this value, we get a value as T is equal to 44 plus 28 into exponential power of minus 0.0996. Exponential power minus 0.0996, we get a value as 0.3693. We can multiply this value with 28. We get a value of T as 44 plus 10.3404. Adding this value to 44, we get a value of temperature of a mineral water as 54.3404 Farad. This is a value of temperature of a mineral water at time T is equal to 60 minutes. This completes the problem. Here is another problem. A body is heated at 110 degrees Celsius and placed in air at 10 degrees Celsius. After 1 hour, its temperature becomes 60 degrees Celsius. How much additional time is required to cool to 30 degrees Celsius? Here first take the given data. A body is heated at 110 degrees Celsius and placed in air at 10 degrees Celsius. That means the temperature of air, that is T naught, is 10 degrees Celsius. At initial T is equal to 0, we get a value of T as 110 degrees Celsius. That is at T is equal to 0, T is 110 degrees Celsius. After 1 hour, its temperature becomes 60 degrees Celsius. That is at T is equal to 1 hour means that is 60 minutes. The temperature becomes 60 degrees Celsius. Here, how much additional time is required to cool to 30 degrees Celsius? That means at the temperature 30 degrees Celsius, how many times required to cool the body? We have to find the T value. For that, the Newton's law of cooling formula is given by T is equal to T naught plus lambda into exponential power minus KT. Now we have to find lambda value. For that, substitute T naught value as 10. That is, T is equal to 10 plus lambda into exponential power minus KT. Call this as equation number 1. Here at T is equal to 0, substitute T value as 110 degrees Celsius. We get as 110 is equal to 10 plus lambda into exponential power minus K into here T value is 0. Here we know that this value becomes 1. Hence we get lambda value as, take this 10 to the left hand side, that is 110 minus 10 is 100. Hence we get lambda value as 100. Substitute this value in equation 1. We get T is equal to 10 plus lambda is 100 into exponential power minus KT. Call this as equation number 2. Next we have to take the data at T is equal to 60 minutes. We can substitute T value as 60 degrees Celsius. That is, at T is equal to 60 minutes, we can substitute T value as 60 degrees Celsius. We get an equation number 2 as 60, which is equal to 10 plus 100 into exponential power minus here T is 60 into K. Take this 10 to the left hand side. 60 minus 10 is 50, which is equal to 100 into exponential power minus 60K. Here if we take this 100 to the left hand side, that becomes 50 divided by 100. We get a value of exponential power minus 60K as 0.5. Taking log on both the side and apply logarithmic formula, we get as minus 60K, which is equal to ln of 0.5. We know that ln of 0.5 value is minus 0.69314. That is minus 60K, which is equal to minus 0.69314. Take this minus 60 to the right hand side, we get a value of K as 0.01155. Minus 60 goes to the denominator. This value becomes K is equal to 0.01155. This is our K value. Once we obtain lambda and K value at T is equal to 30 degrees Celsius, equation 2 becomes, substituting all the values in equation 2, we get as T is 30, which is equal to 10 plus lambda is 100 into exponential power of K. In the place of K, we have to substitute as 0.01155. That is minus 0.01155 into T as it is. You have to find the T value. Here take this 10 to the left hand side, that is 30 minus 10 is 20, which is equal to 100 into exponential power minus 0.01155 T. Next step, take this 100 to the left hand side, that is 20 divided by 100, we get as 0.2. Next step, take this value to the right hand side, that is T is equal to ln of 0.2 divided by minus 0.01155. We get a value of T as 139.345. This is a T value, or we can take it as T is equal to 2 hours 19 minutes. Here 2 hour means 1 hour is equal to 60 minutes. Hence we get 60 into 2 is 120. Remaining is 19. Hence we can take this as T is equal to 2 hours 19 minutes. This is a time taken to cool the temperature of T is equal to 30 degrees Celsius. We get a value of T as 2 hours 19 minutes. This completes the problem. Till here we study about Newton's law of cooling, application of Newton's law of cooling in engineering field, and important question paper problems on Newton's law of cooling. In next video, we study about non-linear differential equation. If any doubts regarding the problem, you can comment below. Thank you.